Now, in earlier parts of this chapter, we found that finding prime numbers is a very important part of cryptography. So in practice, large prime numbers are found using trial and error. So what does that mean? It turns out that prime numbers are not that uncommon. For instance, among 100-digit numbers, roughly every 200 or so will be a prime number. So you randomly try 200 100-digit numbers, and you'll probably find a prime number. Or at least, if 200 is not enough, you try 300, 400, 500. Most likely, after a few hundred, you'll be able to find a prime number. So what you need is a good way to test to see whether some number is prime. And if the test fails, then try again. So if you have a test that you can do very rapidly in a fraction of a second, then it's no problem to test 200, 300, 500 numbers. Okay? So we won't be dealing with numbers quite as large as 100 digits, but we can show some techniques of testing whether a number is a prime number. All right, so one simple method is the brute force method. I can illustrate this with the number 391. Okay? So for 391, how can we tell whether this number is prime or not? Well, let's just go on down the list. Is it divisible by 2? No. So the question is 391 prime? That's the question. It's not divisible by 2. It's not divisible by 3 because the digits don't add up, aren't divisible by 3. Some digits not divisible by 3. Certainly not divisible by 4, 5, or 6. 7 you'd have to check. I don't know. Just keep on going and just keep on checking. And if you can't find anything that divides 391, then you know it's prime. Okay? Question: how far do you have to go? Do I have to check all the way up to 391? Well, obviously that's not true because there's no way that 390 could divide 391. Now, why do I say that? Well, if 390 divided 391, then what would the other factor be? Well, it would have to be another integer. Can't be 1, it would have to be 2. At least 2. But 2 times 390 is much bigger than 391. So if you think about it that way, 390 couldn't divide 391. 389 couldn't divide 391 because 389 times 2 is too big. So actually I could go all the way to something like 200. 200 times 2 is also too big. So I don't have to go even up to 200. 200 is farther than I need to go. So the question is, how far do I actually need to go? Well, that's the content of exercise 41. And to put this in perspective, let's look at an example. Okay. So let's consider the question, I need to check from 1 up to a as factors for n to prove prove whether n is prime. All right, so how large does a have to be? Okay. Now, in general, if n factors, that means that I can write n is equal to xy. All right, now, let's consider the special case where x is equal to y. And I'll just set them both equal to, I'll use the letter a. So that means that n is equal to a times a. Now, of course, here you should be able to solve for a. That's not difficult. Okay. So if we have n equals a times a, according to this special case, and in general we have n equals x times y, that means that x times y is equal to a times a. Okay. So what you need to prove, if x is bigger than a, that means y is less than a. If y is bigger than a, that means that x is less than a. Okay? So you need to prove this. Okay? It follows. Now look, in the first case, y is less than a. In the second case, x is less than a. It follows that at least one of the factors is less than a. What does that mean? That means I only need to check up to a. Why is that? Because if it does factor, one of the factors must be less than a. Okay? All right. So in order to do this problem, you need to solve this for a, and you also need to prove this. So this pretty much takes care of problem 41. Okay. All right, so let's go on to problem 42. The question is, we know that we only have to go so far, we only have to go up to a, but do we have to check every number? And the example is, no. For instance, if n is prime, usually we don't have to divide by even numbers, because if n is prime, you know you're going to be looking for an odd number, so there's no way that an even number could be a factor. Also, once you divide by 3, you don't need to divide by any other number that's divisible by 3, because if 3 is not a factor, then neither is 6 or 9 or 12 or 15. None of those could be factors either. So the question is, how many divisions are needed to test whether n is prime? Okay? So that's the question. Let's see if we can do this just by examining the situation. So this is problem 42. I don't know why it's doing that. All right, so let me just write down the numbers. So here we want to check if n is prime. And here I'm going to check, well, 1, 2, 3, 4. Of course, I don't need to check 1. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and so on. Okay. Now, if I look at the ones that are divisible by 2, and I'm going to take another color here. The ones that are divisible by 2, I'm going to cross out like this. So once I've checked 2, I don't need to check 4 or 6 or 8 or 10 or 12 or 14 all the way down like this. All right, now let's consider the ones also that are divisible by 3. All right, and the ones divisible by 3, I can use a different color. Now this is divisible by 3. Well, let me do it this way. 3, 6, 9, 12, 15, 18. Okay? So divisible by 3 of these. Okay. Now how many are left? Okay. The number left, the number of divisions left. I mean, presumably to check whether n is prime, I'm going to have to divide by all the rest of these numbers. Well, what did I do? I took the total numbers less than a. I subtract out the number divisible by 2. And I also subtract out the number divisible by 3. Okay. Now there's a problem. And what's the problem? The problem is there's some numbers divisible by both 2 and 3. I've subtracted those out twice. So I'm going to have to add those back in again. I'm going to add in the numbers divisible by 2 and 3. Okay. All right, now, and I'm going, so the number divisible by 2, look, every other number is divisible by 2. So you need to figure out how many are crossed out. And we're going up to A. Okay? We're going up to A, and we're crossing out every other number. How many are crossed out? And that's this number here. That's the number of numbers less than A that are divisible by 2. We're going to do the same thing with 3, the same problem. How many are crossed out? And that's going to be this number here. Now, to get the number divisible by 2 and 3, you're going to have to figure out how many are crossed out twice, like this one, this one, this one, and so on. So you want how many crossed out twice. And you want to use this information to solve the problem. You have the total number of numbers that you need to check, and that's up to A. Actually, it's A minus 1, because you certainly don't need to check 1. Then you need to subtract off the number that are divisible by 2. That's every other one crossed out. Then you need to subtract off the numbers divisible by 3. That's every 3 crossed out. And then you'll need to add the number that are divisible by 2 and 3. You're going to have to figure that out. And that's going to give you your result. Okay, so that's how to do problem 42. Hopefully that's enough information that you can be able to do that. Okay, now, this method by which you eliminate factors as you go along, like we eliminated first even numbers, then we eliminated multiples of 3. This method is called the sieve of Eratosthenes, and sieve methods are still very important in prime number theory. Okay, so let's go on to a different method for testing whether numbers are prime. This is called Fermat's method. Now, in the method for brute force, we started at the bottom and worked our way up. But if the prime factors are fairly equal and they're fairly large, that's going to take a long time to get there. Fermat's test goes the other way, starts at the top and works its way down. Okay, so first part of Fermat's theorem is exercise 44, and this is the basic algebraic relation on which Fermat's factorization algorithm is based. So suppose we have a composite number, so it's the product of 2 factors. It might have more factors, but at least we can divide it into 2. Then show that this number n can be written as the difference of 2 perfect squares, which we call x and y. Okay. And there's a very extensive hint here. So I think that you can follow this hint and do the problem. But the idea is that one way of looking for prime numbers, or looking for numbers that are not prime, is find that they're the difference of 2 squares. So if I have a number that cannot be expressed as the difference of 2 squares, that must be a prime number. Okay. All right, now the question is, what values of x and y do we have to choose? And so there must be a starting point where you start checking. So that's what exercise 45 is about. There's actually a minimum value of x that needs to be chosen. So the question here is, what's the smallest possible value of x that needs to be tested? And I suggest the way you do this is look at this equation here and solve for x. Okay? Solve for x and make y as small as possible. Or I should say make y squared as small as possible. And you'll find that when y squared is as small as possible, then x squared will also be as small as possible. Okay, so that's exercise 45. Now, just as in the brute force method, we were able to eliminate some factors that we didn't need to try. Also in Fermat's method, we can eliminate some factors. So we need to prove some factors about these numbers. Remember that we're writing n is equal to x squared minus y squared. Okay, and we can show that if x is odd, then y is even and vice versa. You can prove that using elementary algebra. You can show that for any odd number m, then the square of that number, mod 4, is equal to 1. And that's a useful fact. Now let m equal x plus y. And then you want to show that this expression can be written in this way. And then from this expression, you can show actually that in the case where your original number n is equal to 1 mod 4, then the y must be even. Now, in fact, if the y is even, that means the x must be odd, right? Because if x is odd and y is even, and vice versa. On the other hand, if n mod 4 is equal to 3, then the y must be odd, and that means x is even. Okay. So in fact, that eliminates half of the numbers that we need to check. Okay. So in exercise 47, you do the brute force method. In exercise 48, you do the Fermat method. And here several of the cells are given to you. And you can do the rest of the formula. And you should be able to use that to factor this number. Very large number. All right. Now, once you can factor this number, we've seen in previous exercises that you should be able to find a decoding key for n and e. So use your previous smarts to be able to do the rest of this. Similar problem, part C. Very similar problem. Now, it turns out the primes that are practical are too large to use either the Fermat method or the brute force method. So what happens is they use what are called probabilistic methods. You use a whole bunch of tests, and if the number passes a whole bunch of tests, you don't know for certain it's prime, but you're 99.9999999% certain that it is prime. Now there's some test called the Miller-Rabin test. We won't do the whole test, but it uses some of the following principles. Now here's a fact that we're not able to prove right now. We'll find the proof of this when you take abstract algebra, but it's a fact that's true. If p is any prime number and a is any non-zero integer, then a raised to the p minus 1 is congruent to 1 mod p. This is always true. Okay. So this test can be used as a screening test for prime, because for any prime, this must be true. If I take a number and raise it to the p minus 1, and it's not congruent to 1 mod p, then I know that p is not a prime. So for instance, 15 can't be a prime because 2 to the 15th minus 1 is 2 to the 14th, which is congruent to 4 mod 15. That's not immediately clear, but if you work it out, that's true. But 17 does satisfy this. If I take 2 to the 17 minus 1, that should be congruent to 1 mod 17, and it turns out that that's true. Okay, so those are some screening tests. Now, the definition of pseudoprime is you do this test using a equals 2. So if you use a equals 2, raise it to the n minus 1. If that's congruent to 1 mod n, then it's a pseudoprime, which means it's a candidate for being prime. It may not be prime, but it's a candidate. Okay, so here you'll test out which numbers are primes and which are pseudoprimes. Okay. Now actually, here we use 2 as our base. It's also possible to use 3 as a base. Okay, so here you can use your spreadsheets and your smarts to be able to solve this number. So you've gotten some idea about primality testing And that's the end of this video.